That's so great. So I drank some coffee, so if I'm like, if I use a laser pointer and it's doing a lot of that, that's why. So good afternoon, everyone. Thanks everyone for joining us, whether you're here in person or joining us up on Zoom today for our lunchtime expedition presentation. This month is September. My name is Corey Anco. I'm the interim curator here at the Draper Natural History Museum. I'll give you a little bit more about my background here in a minute, but first, just a little housekeeping. As always, please silence or turn off your remote electronic mobile devices. We just want to take a moment to thank our sponsors, Sage Creek Ranch and the Nancy-Carroll Draper Charitable Foundation, for helping make all of these programs possible. We also want to thank all of you for attending these presentations, as well as for sending in your speaker suggestions. So if you have a topic or a particular person in mind that you think would make a good lunchtime expedition presentation, please feel free to email me. We're always looking for additional suggestions. These lectures are being recorded and they are uploaded to our YouTube channel. So if you go to youtube.com, you type in Draper Natural History Museum, you look for our bear icon, and you will find all of our recordings dating back from 2018 forward. So if you've missed any of the previous speakers, that's where you can go to find them. And if you'd like to be added to our email list for upcoming speakers, just come find me after the presentation. We'll get you down on email, and usually about 2 weeks before I send out just an announcement of who's up next, and you'll get a few more details about that. Speaking of, our next presentation in October is going to be Rebecca Levine with the Meeteetse Moose Ecology Project, so one you don't want to miss. So without further ado, let's get started. So for those of you that don't know me, my name is Corey Anco. I'm the interim curator here at the Draper Natural History Museum with the Buffalo Bill Center of the West. And a little bit about my background before we jump into the presentation. I received my Bachelor's of Science from Lewis University in Illinois. We did not have this building while I was there, but it sure looks nice. So I received my Bachelor's of Science in Environmental Science from Lewis University down in Romeoville, Illinois. Then I went on to receive my Master's of Environmental Management from Duke University, and this was the building we were in. Now they have also a much nicer building there. I'm a glutton for punishment, so I went on to grad school again up at Fordham University. I received my Master's of Science there in Biology and Ecology in 2016. While I was at Fordham, I started working with the American Museum of Natural History. And this is really what kind of began my passion and interest of working in natural history museums. I was fortunate enough to have a really fantastic group of mentors there that helped me walk me through the process of things like DNA extraction and analysis. And so what we did was we started looking at the genetic diversity housed in museum collections. And for that project, I extracted DNA from leopard skulls. And what was really cool, we were looking at African leopards, was that this is the first work in about 20 years or so that re-examined continental scale genetic diversity in African leopards. So I'll quickly kind of walk you through what you're seeing on the screen here. We discovered, looking at DNA sequences, that African leopards harbored far greater, at least mitochondrial genetic diversity than was previously suspected or reported. And it's museum specimens that were the key to this mystery. So every single circle that you see here is a DNA sequence. And when a circle varies and you see a hash mark, that's the number of mutations that separate one DNA sequence from another. So for example, when we see over here and we have 4 or 5 hash marks separating, that's the number of mutations that separate those particular DNA sequences. So what was really cool is when we plotted this by geography, we found that, hey, there is a geographic relationship to these genetic populations. And that's really what ignited my interest in looking at museum specimens, working with natural history museums, is that there's these larger landscape level processes at play that are influencing not only the distribution, but the diversity of organisms. So we see that looking at the map here, that West Africa and Central West Africa here tend to be more genetically distinct and clustered than you would see in other areas. So this work was published, graduated, and then from there I was kind of pretty interested in saying, hey, I want to stick with the museum thing. This is pretty neat. So fast forward, I was fortunate enough to be brought on here at the Draper Natural History Museum, and it's just been a crazy wild ride since I began working here in 2017. And I can confidently say that there's been no shortage of excitement, from aerial surveys to look at golden eagle territories, to rappelling into nests to collect prey remains, to picking up frozen carcasses from the Wyoming Game and Fish Department, and then preparing those carcasses with an incredible but incomplete list of volunteers here. It's been fascinating. It's been fun. It's been challenging. It's been great. But nevertheless, we're always staying busy at the Draper and the Center of the West, which really brings me to the focus of today's presentation. So I want to take the rest of the time today to discuss a couple really exciting projects that we poured ourselves into and undertook over this year. So without further ado, let's get to it. If any of you visited the center between mid-June and mid-July, you likely had the opportunity to witness us reconstructing a couple skeletons in the Seasons of Discovery Gallery in the Draper Natural History Museum. That's over by where the old south entrance used to be. So with generous grant support, the Draper and the Center of the West hosted a skeletal articulation workshop. This was intended for staff and volunteers, and it featured Lee the Boneman Post. So just a little bit of quick background. We have 4 primary areas that we focus on in the Draper. There's collections. Those are the things we think of when we think of specimens. There's programming, so something like this, or education outreach with the public. There's the exhibits, the traditional thing you think of when you think of natural history museums. You walk through the galleries and you see the exhibits. And then there's research. So this was one way we were looking at how can we take our collections and make more of them? How can we bring that out into the public face a little bit more so that it doesn't seem like this black box behind closed doors? What do we do with bones? So this was an opportunity. Let's build a skeleton. The Draper turns 20 years old this year, has turned 20 years old this year. Like, let's do something really fun and exciting with the public. So we wanted to bring Lee in here and do this in front, reconstruct it for everyone's eyes. And in the process, we wanted to learn this skill set. We were then going to take this skeleton and install it into the exhibits. So it's a way we're using collections and programming and outreach as well as exhibits. Lee brings over 40 years experience articulating skeletons. He's self-taught. He's remarkable. He's done over 70 of these articulations. And the guy has literally wrote the book on the subject. And so, we figured what better way to really kind of celebrate the Draper turning 20 years than to let's do something fun, let's do something special, and let's engage as many people as possible. So that's what we did. And if you weren't able to join us while Lee was here, don't worry, I'll walk you through as much of it as I can without spending too much time on it, because there's a ton of details and I'm going to gloss over a bit. But I'll show you how we reconstructed these skeletons in about 2.5 weeks. So first, the bare necessities. Where did we get it? How did it arrive here? The Draper is a salvage-based institution, meaning that with rare exception, we don't collect anything from the wild. That means all of the specimens housed in our collections come to us from one of a couple means, either salvage activities that were permitted through the state and federal agencies to collect things. That could be a bird that hits a window, a vehicle strike, dies in a fence, any other sustained injury that leads to the mortality of that organism, or it could be a transfer. Transfer could be something like an organism that was poached, and once that case goes through evidence and the carcass is no longer needed, it can be transferred to us. It could also be transferred to us through nonprofits. We work a lot with Ironside Bird Rescue, and so if a bird sustains injuries beyond the ability of that animal to be rehabilitated, it may die from those injuries, it may be euthanized. In those cases, it can be transferred to us to be used in our education and research collections. When wildlife have a perceived or a realized threat to human safety or property, sometimes the difficult decision is made to lethally remove that animal from the wild. If that animal cannot be relocated or put out of harm's way either to itself or to the public, sometimes that difficult decision is made that that animal needs to be removed from the landscape. So the animal has 2 destinations then. It either goes to a landfill and it decomposes there, or it can go to some kind of repository to be used for education and research. And that's really what we are at the Draper Natural History Museum. We have an educational collection, we have a research collection. So it's really our goal to leverage these organisms and give them a meaning and a value to society and science beyond life. So we have a phenomenal relationship with the Wyoming Game and Fish Department. And when they had to make the decision to remove this 14-year-old male grizzly bear, they gave us a call and asked us if we could use it. And whether I have a plan or not for something, my answer is always yes, and then we figure it out. So when we got this bear in 2020, this was our first complete skeleton or first complete carcass of a grizzly bear. So naturally, we were going to prepare the whole thing. And later on, the idea came down the line of, let's see if we can articulate this sucker. And so to do that, it's an incredibly lengthy process. Preparing a specimen for articulation. Articulation is just a fancy word for reconstructing. Think of it as like adult Legos. You're just putting the bones back together. It's a really involved process. First, you need to deflesh the animal. That means remove the skin, and then you're removing all that soft tissue. Soft tissue are things like muscles. And we need to disarticulate it because it's a really big animal and it's unlikely. We have volunteers that are working with us on Tuesday mornings, usually for about 3 hours at a time. We've gotten really good at this to the point where now we're able to process a full body specimen pretty darn quickly in 1 or 2 weeks of work. But back when we were doing this was multiple weeks of freezing and thawing, limbs at a time, and really kind of working down and getting rid of all that soft tissue. But we can't get everything. We can't get everything with the scalpel blade. There's still going to be some muscle tissue on there. There's delicate areas inside the nasal cavity, inside the skull. The vertebrae are really tricky to get a scalpel blade all around, so we have to recruit something else. And we leverage the hardest working employees at the museum, dermestid beetles. So you think of a dermatologist, that's somebody that studies skin. Dermestid beetles are skin or flesh-eating beetles. They work around the clock. They are amazing. They never ask for a raise. They do the best job. And when it's all said and done, they just clean these things immaculately. So we were fortunate enough through grant funding to build a dermestarium facility. We've always had dermestids here at the museum, but they've never had their own permanent facility. And through grant funding, we were able to build that facility. And they've never been happier. They're flourishing. We've had this colony for more than a decade. It's been great. And so once the beetles are done with their job, we're still not done. The bones then have to soak. They soak in a couple different solutions. The first solution is ammonia. Ammonia is a degreasing agent. You stick the bones in there, and it starts to leach out things like the fats, the lipids, the marrow inside the bones. It's amazing how greasy bare bones are. We soaked this thing for probably 8 months, and we're like, all right, they're pretty darn good. Turns out we were wrong. After Lee got here, we had to simmer them for about 24 to 36 hours in warm water to leach out the rest of the fat. The reason being, adhesive won't stick to lipids. So as you go to drill and pin and glue bones back together, the fatty tissue that's leaching out of the bones will prevent those bones from sticking or to the adhesive or sticking together. So between the volunteers, the beetles, and the ammonia, it took over a year to prepare the skeleton, and they were still too greasy. You never want to boil bones if you're interested in retaining the original function and integrity of those bones, because a couple bad things happen. This is a mountain lion skull here. The skull here on the left was prepared with beetles. The skull here on the right was prepared by boiling. If you look at the sutures that bring those bone plates together, they begin to separate in the boiled skull, and the reason for that is increases in temperature and pressure. As you heat things up, what does it do? It expands. So that's going to cause some of that skeletal tissue to start to separate. Furthermore, some of those skeletal structures are really porous, highly vascularized, very fragile. So your nasal conchae or your turbinates, they're completely intact in the skulls prepared by beetles. They're completely dissolved in ones that are boiled. So when it comes to how are we going to leverage, how are we going to use these specimens in decades to come, technology advances at an exponential rate. There's no telling what we're going to be able to learn or examine or detail from these organisms as we progress with technology. You think about the structure of DNA in the 1950s. We discover it then. Rosalind Franklin takes a photograph and we say, hey, this is the structure of it. You fast forward 70 years with cloning organisms. That's mind-boggling. So when you think about something like this, I wouldn't be surprised to just throw out there that, hey, in 20, 30 years, we can have a scanner that looks at this and you can tell relatedness between species based on a fingerprint. There's really fascinating, crazy stuff out there. The other thing with boiling that's bad, teeth crack, teeth fall out. Again, the separation. So it's a lengthy process to do it with the bugs, but they do the best job of doing it. The other way you can do it is macerate it, and that just simply means you're going to take a skull, same thing, you deflesh it, you get off as much muscle tissue as you can, and you stick it in a kettle, just let it sit out in the sun in summer and let the bacteria do the job. They'll get into the pores of the bones, and they'll consume that fatty tissue. And if you leave it long enough, the bacteria will die off too, and you'll just be left with tea-colored water and bones. So back to the old articulation. With the bones finally ready, we began the process of assembly, beginning with the vertebral column, which meant we were spending a lot of time drilling holes into the bones, drilling holes into all the vertebrae, and that's to allow different attachment materials to slide through and to fix these different pieces back together. Lee later informed us that he always starts with the limbs, not the vertebral column, so we definitely did it backwards. But hey, we like a good challenge here, so why not? Our team consisted of a mix of Draper and center staff, interns, and volunteers. These people were amazing. We worked 6 days a week, about 10 to 12 hours a day for 2.5 weeks, nonstop to do this. It was a rotating cast of characters coming in each day. Some people were available for multiple days. Some people were available a couple hours here and there. But everybody kind of banded together to make this happen. We never really knew who was going to work on what that day. It was going to be like, we need 3 or 2 people over here. You're going to work on this limb. You're going to work on the hand bones. It really took a whole team to pull this together, and I couldn't be more grateful for the enthusiasm and also the effort and the initiative that was taken by everybody that was a part of this project. We also contracted a local film crew. The only reason I have great photos of this is because of this film crew. Dan and Vanessa to document the articulation process. So they took a ton of photos. They also took some videos that will be forthcoming. And we gave them a chance to jump in. They didn't hesitate. They went and purchased supplies. They helped us build stands. They got right involved with either the silicone, with the bones, the drilling, you name it, they did it. They were every bit a part of this team as any of the staff or the interns or the volunteers were. Again, I mentioned we're a salvage-based institution, and we get a lot of our carnivores. We get almost exclusively, we obtain our carnivores from the Wyoming Game and Fish Department. They're wonderful to work with. They've always been really big supporters of us. And so when we had the opportunity to involve them in this process to come full circle, we had Luke Ellsbury come out and got him involved in drilling bones. And so it's only fitting that they got in on the fun. While reconstructing the bear, that was our primary goal, but we figured, well, we might have enough support. Is it possible that we could do 2 specimens simultaneously? So we also started a mountain lion. This was about a 2 to 3 year old mountain lion, and doing both simultaneously, first focusing on the bear and then directing a lot of attention and resources and personnel to the mountain lion, we were able to pull off both specimens. Sometimes working after hours, after everybody else is gone, we still need a couple extra hands. So some of the security staff would be on patrol and I'd yell, hey, come here a minute, we need you. And they were always more than happy to jump in and help out. So with the 2 skeletons going, there was ample opportunity for everyone who wanted to be involved to be a part of this process. I mentioned this was about 10 to 12 hours a day, 6 days a week for about 2.5 weeks. Lee calculated his own time on it was about 700 hours or so. You factor in everybody else, and there's an awful lot of time that was spent putting these skeletons together. But one of the real highlights for me, I mentioned again, this is collections, but one of the real highlights for me with this project and as an artist in residence program here was beyond acquiring the skills to articulate and do this process with additional specimens here and acquire those skill sets, it was sharing the process with the public. Adults and kids alike were thrilled to interact with us, be a part of this, and in some cases help with the articulation. And I say that as soon as I saw this next photo, that if I never got a single other photo from Dan and Vanessa from this project, that this is the award winner for me. I mean, she was just like absolutely floored to get to hold this mountain lion skull. And then when I asked her, did you ever think you'd walk into a museum and just get to hold a mountain lion skull? She goes, yeah. I'm like, good for you. You're a future curator. We had a variety of local and regional visitors and a surprising number of international tourists that came out to see this, whether they stumbled upon it, and several of them had seen it on the Billings News or local news outlets and said like, hey, we saw this was going on, when you want to come check that out. And that was really cool. That was really exciting to see that the word was getting out and people were interested in seeing this. It encouraged us to consider looking at other programs that we can do to leverage and highlight this. So while the skeletons have been articulated, we're not quite finished. And as we speak, the center's own Jeff Rudolph is working to fabricate a professional mount. And we're really excited about what this is likely to turn into. And a quick plug here, Jeff is currently the artist in residence for the Whitney Western Art Museum until tomorrow. So if you get a chance, run up to the art museum after this, find Jeff, see what he's working on. He's an incredibly, insanely talented fella, and he's doing some really neat stuff. And our plan for this is to take the post back here, and we are going to turn this into a tree because this is intended to be a grizzly bear scratching its back on a tree. So Jeff is currently working on a mock-up of this, and it will have, we're hoping to have some roots being pushed out of the ground and make this really look something neat and special with a couple extra Easter eggs. And eventually, once this is done in the next, hopefully 2 to 3 weeks, this will become part of the Draper galleries and exhibits, so you'll be able to see it on display. So let's see, timing-wise. The Articulation project combined collections, exhibits, and programs. So I mentioned there's a fourth component here that we really focus on at the Draper, and that's research. And so the next part of this presentation is really going to look at this pilot program that we've launched to explore bats in the Absaroka Mountains. But first, why bats? What's so interesting about them, and why should we spend our time working on them? Well, first off, they're an indicator species, meaning their presence and their distribution on the landscape gives us clues as to the health of that ecosystem and landscape of what species it can support, particularly if those species are sensitive to disturbance. Wyoming is home to 18 species of bats, 11 of which are listed by the Wyoming Game and Fish Department as species of greatest conservation need. What that means in a nutshell and broadly speaking is that we have very little information about the distribution of these organisms, where they are, where their populations are at, and if there's any threats such as white nose syndrome, if that's making its way continuously west, which is a fungal pathogen that will decimate bat populations. So they're data deficient, meaning it would be really helpful from a management standpoint of wildlife and natural resources to know what's going on with bats. So there was a data gap. There was a need from the state agency and federal agencies for threatened and endangered listed species to find out what's going on with these guys. But there was no personnel to do it because of the remote location and nature of this work. They're understudied relative to their charismatic megafauna counterparts. I often joke about bears and insects that for every bear, there's probably 10 bear biologists, but for every entomologist, there's probably, 5,000 insects, so there's a disparity there between the amount of resources that are being put on some of these lesser known or lesser studied, or maybe perhaps in some eyes, less interesting species. So it was a niche that we could fulfill that no one else was working on. It's unlikely that if we were to launch a research project here at the Draper on wolves or bears that we're going to discover anything new that's not already known by the state or the feds. So we want to apply our efforts where we can make the most impact. And also, if you go through the Draper galleries, this is a species This is the only mammal, fully flighted mammal, and we don't have representation in the Draper. We have a handful in the collections, but we don't talk about them. But they're a major component of this ecosystem, and it's kind of out of sight, out of mind. They're nocturnal. You don't really see them a lot. So there's a lot that can be story-wise pulled into the Draper and pull into the exhibits and really kind of tie this Greater Yellowstone ecosystem a little bit more cohesively together. So why mountains? Similarly, these are super fragile ecosystems. The alpine environments above tree line, they have alpine meadows, alpine flowers, very sensitive to disturbance, very dependent on hydration, water, snowpack. And when that shifts, these are indicator ecosystems as well. So if an ecosystem is very fragile to disturbance and we can note or document that disturbance, that may have downstream impacts on those wildlife and those wildlife communities. Again, they're understudied or in some cases unstudied due to the remote nature of these systems. It's pretty difficult to get back there if you don't have something like maybe an ATV where trails are accessible, horses, a lot of time and steady legs. And the equipment can be cumbersome. Each sensor is about 20 pounds. And so when you factor that on top of your layers, your food, camping equipment, if you're going to be out there for multiple days, it's pretty difficult to get back to some of these places. So, there's a reason that no one's really popping a whole lot of sensors up in the mountains. And looking at gradients, they give us information on habitat preferences. So what do I mean by gradient? The goal here was to look at the mountain landscape and deploy, and we'll get into this a lot more detail soon, but deploy these sensors every couple hundred meters up the mountain. And that's to tell us a couple of different things about as you increase in elevation, the environment, the landscape changes, different vegetation communities persist at different elevational levels. Some of that could be due to sun exposure, some of that could be due to access to water or the quality of the soil that it's growing on. But you have this very diverse or heterogeneous landscape that facilitates different vegetation communities. Different vegetation communities facilitate different wildlife communities. So we want to look at how does the landscape change? How do the bat populations or bat species that are represented, bat species that are represented in those landscapes vary? And then we also want to look at big picture connections. And I'll get into this a little bit more, but we know that moths are a really important food source for grizzly bears. If any of you attended Frank Van Manen's talk earlier this year, you noted that he mentioned the statistic of bears can consume 40,000 moths in a day. 40,000 moths being a half a calorie a moth is 20,000 calories. So we know they're a really critical food source for bears. Is there a link between bat and moths? We don't know. Maybe, maybe not. Maybe there's no bats up there at all. We don't know because no one studied it. So that was the goal, is to kind of look at these different things. But then also, are there these bigger picture linkages? So quickly to introduce the team here. The research team consists of 4 co-PIs. PIs is just principal investigator. On the left here, this is Katie Goodwin. She's a wildlife biologist, and when she's not spending her time on the Absaroka Bat Census project, she's working on other bat projects. So while this project is not part of her normal work, Katie is monitoring bats with the North Dakota State University and the National Park Service. This is Jordan Harrison. He's an ecologist with West Consulting Group. This is Dr. Jason Rigia. He is a postdoctoral scholar with the Museum of Wildlife and Fish Biology at UC Davis in California. And then, of course, that's me. So year 1 is our pilot year. Pilot year meaning, hey, we're just going to take a stab at this, see what we get. We might get data, we might get nothing. We're not sure. This is the pilot. And what we want to ask in this first year is, are bats using alpine systems? Are they there at all? We might deploy these sensors, find nothing. We don't know because no one's done it. If so, if they are there, which species are there? In western Wyoming, we probably have about 9 of those 18 species found throughout the state. So we want to know, are any of them there? And if so, how high are they? Where are they at? Is there an elevational limit? That's a big part of this, is to what point do you stop seeing life or stop seeing these bat assemblages? And we also want to look at, again, with the gradient, as the vegetation communities change, what vegetation communities are influencing bat distributions. Do you have a greater diversity of bat species at a certain vegetation community, or is it consistent across the gradient? How are they using the landscape? Should this work continue on to years 2 and 3, there's a couple additional things we want to look at. Assuming that we get data from this, we start getting presence localities of known locations, GPS coordinates with set elevation and set habitat types. We want to start modeling that. If you have a known set of locations, you can use that as predictor variables for, okay, this habitat exists here, and we found bats here. This habitat also exists over here. Are there bats there? Model might say we have high prediction that sites A, B, and C here also would support these species. So that would warrant the ability to then say, okay, we want to examine, we want to study, monitor these sites to see if we're seeing the same representation that we have in confirmed locations. And then to really answer that question of, is there a link between bats and moths? Year 3, we would like to try to collect some bat species, look at stomach contents, and confirm whether or not, are they consuming moths? Are moths an active part of their diet? Are these sites important to the distribution and sustaining the populations of these species? So how are we actually doing this? In year 1, we deployed 2 types of sensors. We had 6 Pedersen units and 2 SM4 units, song meters. And they work very similarly. The way these are kind of orchestrated or fixed is that the sensors sit in an ammo can. These ammo cans try to help kind of shelter the sensors from the elements, as well as try to prevent them a little bit from being tampered with by the wildlife. This is what a typical sensor station looks like. Extending out of the can is a cable. This cable is wound up the pole here. It gets a little bit higher than some of the clutter. Clutter could be anything that obstructs a signal. And attached at the top of the pole is a microphone. And that microphone is set to trigger and record after sunset from dusk until dawn, essentially. And every time it hears a sound within a given frequency spectrum that falls in line with the call of a bat, typically above a range of human hearing, it will start to record. And it will record for maybe a 10 or 15 second interval. And as bats are flying around and echolocating, it will deposit those recordings onto SD cards or compact flash cards. So again, we wanted to deploy these sensors near creeks. The reason being is that bats, all life as we know it requires water to survive. So bats are no different. They're going to need to drink water, but insects are probably also being near the water as well. So we wanted to deploy them near creeks, thinking that's going to give us the best opportunity to monitor them or pick them up if they are there. So they were deployed along creeks and then again on an elevational gradient, which gives us a few vital pieces of information on what elevations are we finding bats and what vegetation communities do these bats prefer. Again, I mentioned the whole environmental heterogeneity concept. It refers to the diversity of the landscape and vegetation characteristics. We had stations deployed in forests. We had them deployed in intact and burned forests or meadows as well, alpine meadows with wildflowers, thinking that the bats are going to go after insects that are pollinating those flowers at night. And Telus fields, to name a few. So we had a wide diversity of different landscapes in which we were deploying these as we went up. And each sensor weighed about 20 pounds, which combined with camping gear meant our packs weighed on average maybe around 50 to 60 pounds. So with 8 sensors, that's an awful lot of weight, which is why I'm incredibly, incredibly grateful to, beyond the researchers that helped with this project, all the volunteers that jumped in and signed up and assisted with this project for carrying equipment in and out of the mountains. And honestly, we wouldn't have been able to pull this off, pull off the pilot study if it wasn't without them. And even though the landscapes were beautiful, the work was demanding and at times brutal. So I'll just share a couple of instances of where we had to adapt on the fly. The first was the very first deployment that we went out with. We tried to get out as early as we could, but for anyone that spent quite a bit of time in the mountains, you know, afternoons mean thunderstorms or higher probability. So it was about 10 a.m. On our first deployment, and we had gotten up to about our fourth site, and it just was getting really ominous. The clouds were really thick, and we just got caught in an electrical storm. There was no cover. We were essentially at tree line, which means you're also kind of the highest point. And for those of you that avoid lightning, you don't want to be the highest point because it's going to follow the path of least resistance. So as we were getting hailed on, we separated and we just sat there and took it for about an hour and a half, hail and rain, and just got really cold and, you know, just sucked it in. And once we decided it was still raining, but it was light enough that if we stand around, we're just going to be here all day. We just kept going. So that was our, you know, introduction to the project of here we go. And attitudes were challenging at times. You know, it's difficult to be hungry, cold, and wet, and still have like another 8 hours of work to do. Another one of braving the elements, we had gotten up to our site, and Brian was here for this one. We had gotten to our site and we saw the clouds rolling in. We knew we were going to camp there for the day anyway, so we just set up tents. And I'd say probably within a half hour of us getting the tents up, we just got hit with some hail. And so the hail didn't last too long, but it rained for about the next 10 hours that day. And that was the first of a 3-day trip that we did about 35 miles in 3 days. And it was wet boots every day. But, you know, there's no better office to have, in all honesty. We also, there we go. It's a little tricky with the multimedia. Another really cool thing that happened to us was we got to our campsite on the first deployment, on our our last deployment, our last field site. And within 2 minutes of getting there, we had a couple adult golden eagles come in, and right in front of us, they never saw us. They dropped this ground squirrel right in front of us, and then coming right behind them is 2 juveniles. And again, they didn't see us either because we were just in a clearing on the edge of a forest. Comes through the trees. It's probably about 20 feet above Jason's head. You can hear the wind rushing through the wings as it came in. Talon's first coming after this thing. It sees us, it freaks out, it flies into the forest, and the other 3 fly off. And again, like there's no shortage of what you're gonna, what you might encounter, what you might experience out there. And on our last retrieval, we ran into 13 grizz, a couple wolves, and some elk. And so as we were going up over a pass, we were trailing a sow with 2 cubs. So that's the sow and 2 cubs here. And we got up on the ridge because down below over here was another couple bears. So we got off the trail and just started to head up thinking, okay, we're going to give ourselves plenty of room and be clear. But they were going where we needed to go. And luckily, every bear that we encountered was a good bear. If they saw us, they ran. So, you know, we were very fortunate that we never had any issues, but we always kept group sizes up. And, you know, vigilance is kind of the name of the game when you're out in the backcountry. So while most sensors were intact and untouched upon arrival during retrieval, there were a few that were investigated by the local fauna. I can't say definitively, but I'm pretty confident that these were both tampered with by bears. They're staked into the ground, so the stakes have been ripped out. And it's likely it just leaned up against this to try to scratch. It's something new in the environment. They're going to investigate it. They probably patrol these territories quite frequently. They know everything that's there. When something's new, it has a new smell, they're going to check it out. The worst instance was in the Tellus field. where we came up on it and we realized our sensor was bent in half. And this is so far back here that I know it wasn't another person. If you look at the sensor, the pole's bent in half, the cable's ripped out of the box, and it's upside down. So this one was definitely tampered with quite a bit. But still, despite any of the complications, despite any of the elements, I'll take a day. Despite any mishaps, I'll take a day in the office here any day of the week.
All right.
I mean, I don't know if I can, the video doesn't capture it, but I don't know if I can accurately describe just how gorgeous the Alpine is. If you ever have the chance to spend some time there, do it. You can access the Alpine on the Beartooth Highway. You're driving above 10,000 feet. It's otherworldly, and it's good for the soul, so do it. So how do these sensors actually work? I talked about how we deployed them, talked about why we deployed them where we did, but what are we actually getting out of them, and how does this actually work? So every vibration generates a sound wave. Some we can hear in the spectrum of human hearing, some are sub-frequency or subhuman hearing, some are ultra-high frequency. Sound waves have distinct shapes. No surprise, if you, birders will identify birds based on their calls, and if you listen to a blue jay versus a robin versus a raven, they sound differently. So if you were to record and visualize that call, it would have a different shape, a different sound wave, and that's exactly what's going on. So what we see on the right are the calls of different birds and the shapes of them. And that's what it looks like when you record it and you visualize it on a spectrogram. So nearly all bird songs are within the spectrum or the range of human hearing, which is typically 20 to 20 kilohertz. I don't know every single bird in the world, and I don't know if they've ever all been fully discovered, but there's some that may be above, but the overwhelming majority of bird songs are within our spectrum of human hearing. And as we age, our ability to hear these high frequencies at 20 kilohertz or so starts to decline. So being able to capture things on microphones and play back those recordings and slow them down and bring them into the spectrum in which we can hear them really helps, really aids our capacity and our ability to analyze some of these calls that otherwise would be gone unheard. Echolocation is the means by which bats navigate. While they are not actually blind, they have highly sensitive vision. So their primary means of navigating through the landscape, through the environment, is through calls. They emit a signal, they emit a call, and that vibration bounces off of something and comes back to them. Depending on the size and the time, the delay it takes for that vibration to reach them, that sound wave to reach back to them, they can detect how far away something is and how large or small an object is. And so just like bird songs, bat calls have distinct shapes as well. Again, I mentioned bat calls are frequently above the spectrum of human hearing. And again, they're nocturnal animals. So these two factors combined make it really difficult to identify a species without artificial aids like software and recordings. So ultrasonic recorders like the kind that we've deployed helps us to do this, helps us to visualize these calls and then identify species. So you can see the different kind of shapes here, some kind of more of a classically described as a hockey stick pattern versus more of a vertical dash. And so these software programs slow down these calls, separate them so we can kind of see the frequency at which they're emitted, the distance at which they're emitted, and help to visualize these calls, revealing the wavelength shape and really the signatures that can be categorized by shape and assigned to different species. And so the big question is, did we find anything? This is all super preliminary. I sent off a hard drive to one of our PIs last week, and he cranked this out about 2 days ago. So we're still kind of digesting the information, but I'll point out a couple of things. We're 100% confident that we have bats. We know that. we're pretty darn confident that we have at least 4 species, maybe up to 7 species here. The 2 that are highlighted here, what you're seeing with the numbers here, that's the maximum likelihood or the probability as determined by the analysis software that call can be assigned to this species. So seeing something like this, that's fantastic. And this is a really special one that we'll talk about here in a minute. But the ones highlighted here in orange indicate, hey, this is pretty low probability. It could be noise. It could be a misclassification. There's not certainty with a few of these. These 2 can be easily confused at times. So there's a lot of manual quality control checking with a couple of these calls and a couple of these species. Quite a few of these calls and a couple of these species. So we have these kind of split as low frequency organisms and high frequency signals. Low frequency meaning lower on the edge of the spectrum of the frequency range, and higher being much more ultrasonic. Spotted bats are really important because they are one of those species of greatest conservation need. And the reason that you're only seeing it at a certain elevation, not a kind of across the spectrum, is because spotted bats are typically only found at the higher elevations. And they are bats that specifically roost on high cliffs. This is really high for this species, 3,200 meters. And it's a really interesting find if we validate this and we find out that this is true. And the last component of that is spotted bats are one of the species that does consume moths. So moth sites tend to be at really high elevation. So we have spotted bats at high elevation. This link might actually exist. And if it does, that'd be really fascinating. If we look at what species are we seeing based on habitat type, as we deployed the sensors and we're filling out the data sheets, we also took a survey of the surrounding landscape and tried to classify what does the vegetation community, what is it comprised of here. And so again, when we look at some of these, we're seeing kind of characteristically the spotted bats are up in the alpine and they're hanging around these meadows and these talus fields. What do bats or what do moths need to survive? They're going to get nectar from flowers. Flowers in the high elevation areas are going to come from the meadows. So there's other components of this that are lining up nicely to suggest that there may be a possible link here. And what's really exciting is that we're seeing a diversity of species. Now we still need to refine this. Again, this is all preliminary data. But the really neat thing is for a shot in the dark, not knowing what we were going to get in an area that's never been monitored or surveyed for bats, we found bats at every site. So that's really, really exciting. So where do we go from here? We've finished the field season, the pilot year for year number 1. So we need to refine these analyses. We really need to take a deeper look. We need to kind of manual quality control vet a lot of these, and we need a second opinion on that. That'll be another one of the PIs that tackles that. And then we may want to expand these study areas, both in elevation. If we have not hit the elevation limit, meaning the highest point in which we've detected bats at, we've not hit the limit. They're there. We want to try to not find bats. We want to try to go as high as we can to the point where they've stopped. We've found where they've reached their limit, where the community there, the environment there cannot sustain life for bats. So we want to determine the elevation limits and really potentially look at additional sites that have not been included in this initial study. For years 2 and 3, we want to take those data and we want to model species distributions. If we find them here and we're really interested in the management and the concern over some of these species of greatest conservation need, it would be really helpful to know, okay, these are the habitat preferences, these are the elevation ranges. These things also exist at sites A, B, and C. Where else might we find them? What other populations may exist? So that really helps from a management standpoint. And if that link does exist between moths and bats, collecting a few specimens for the collections here can help us tie that link together and definitively and quantitatively say yes, there's a confirmation that there's a link between moth aggregation sites and bat foraging grounds. So there's so many people that have made both of these projects possible. I'm not going to go through a name list here because I'm going to leave folks out. But it's everything that we do at the Draper, everything that we do at the center, in all honesty, is supported and made possible by the community that's a part of these projects. That's really a part of what we do. I'm incredibly grateful and blessed to have such a wonderful cohort of people, whether they're the volunteers, whether they're my coworkers, people in the community that just want to know about something or offer a lead on things. It's been great to see so much flourish because of everyone's contributions. So we're really just excited to see where the rest of this goes, and if we continue on for years 2 and 3, what other things we might find. So that said, I'm happy to take any questions, comments, concerns you may have. Thank you.